Good day everyone and welcome back to the channel. This is going to be a short video. Might not be too short, but it's not going to be, it's not going to be my usual really long content. Well, I guess my video is a mix of anything, but anyway. A few people, not just the commenter in one of the last videos, but I mean, going back, the 15, 20, whatever videos that's been on designing this amp. People have asked all sorts of questions to leave in comments, such as like, what are your goals with it? What are you trying to do with it? Before you make it better, why not get it working first? You should have breadboarded it first. Just heaps of different, some things are more comments, some things are actual genuine questions. So I thought I'd come on and address all that. So I'll just go grab an output stage. So a few years ago, I came across the SAP series, SAP 15 Sanken devices. They've got the integrated diode string in the devices. And I've got these heat sinks with this interesting cut and transistors mount on the top, yet somehow it wicks all the heat down the bottom of the heat sink just as much as it rises. However, right here the temperature is quite accurately the temperature that is here within a few seconds. So, and I trialed all different diodes to find diodes with a good temperature coefficient with a couple of milliamps running through them that would track thermally well. So I did that. Originally it was 2SC 5200s and 2SA 1943 transistors and tip 41, tip 42C drivers. What I did then was I kept lowering the resistance of these resistors and increasing the capacitor value until there was literally like no cross distortion, not crossover distortion, cross distortion. I came up with my little bias network. Added base resistors, 2.2 ohm base resistors to all transistors, 10 ohm base resistors to the drivers, 0.22 ohm low inductance emitter resistors, high quality components for the Zabel and all that. So I designed that years ago. It wasn't with all the high quality components, I just recently upgraded the components. Then I looked at my schematics that I had lying around for the original design of that, because I designed the drivers, the pre-driver stage as well, and the front end. Let me just, excuses for being so messy, but originally this was basically what I had. So it was the two outputs per side, the 0.22 ohm resistors, the Zabel, 200 ohm resistors across the bases. Then just ignore those caps, I never fitted them. 10 ohm base resistors on the drivers, two 430 ohm resistors between the bases of that with a cap across that, and then pre-drivers, right? But the pre-drivers had 27k resistors going from the rail to a 500 ohm pot to their base on each side, and a diode string in the middle with a 4.7 microfarad electrolytic cap, a 1 in 4 0.7 anti-protection diode, and the string of bias diodes. That was the amp. You'd set the bias by adjusting these resistors. 27k was enough current to provide drive and bias, and then the two 500 ohm pots would allow you to set the offset to get exactly zero offset, and then the bias strings got its adjustment pots in the middle. That was the original design. I was running off of a Singleton Class A capacitively coupled amplifier, had feedback going to it. I just had this resistor here split into two resistors, and the center point was going to a 10 microfarad film cap with a 22k resistor to ground, and then that was going to the Class A VAS / input stage, all in one transistor, which was running 15 watts on a heatsink to provide the drive in Class A. Then I looked at Doug Self's, I hate calling it Doug Self's Blameless amp because it's honestly an old late 1970s design that he just claims is his, I guess. But anyway, that's why I just say the Blameless. I looked at that and I liked a few things about the input stage and current sources up the top and that. But then most of the amps I'd seen people build were just a single current, like 2 transistor current mirror at the top, single input pair, shared current sources. I looked at all that and I was like, I can improve this input stage so much, get way better rejection from the rails, more gain, better linearity, higher slew rate. So, and no chance of the vast current source and the input stage current source being affected by each other, whether it be oscillation, noise coupling, audio coupling, just their current and voltage varying because they're sharing the same reference, none of that. So I made 2 current references, one for the VAS, one for the input section. Made the input pair complementary feedback transistors, and I added a 4 transistor current mirror at the bottom. So we've got ridiculously low offset, really good slew rate, really good gain. Then I did a lot of research into the feedback network, and it's usually just traditional Miller. It's just 47 to 100 picofarad cap between the collector of the VAS transistor to the base of the beta enhanced transistor. Sometimes that's done using 2 capacitors, say 200 picofarads or 220 picofarads, tapped off at a midpoint with like a 560 1K resistor going to the feedback line. Sometimes it's done like that going to ground, but the capacitor values need to be different. That's 2-pole compensation. So I studied all these different compensations and I worked out the output inclusive 2-pole traditional Miller compensation is the best. It's literally everything. You've got capacitance from base to collector of your VAS transistor and beta enhanced acting as your traditional Miller comp. You've got the center point going to feedback, so it's output inclusive, and it's also going via another resistor to ground, so it's 2-pole, so it's everything. And yeah, you have to work out the values of the resistors and the capacitors to make it work, but it's really good. I looked at the feedback line, and a lot of people just have a resistor, 15k, 10k resistor. Some people put, say, 15 picofarad, 22 picofarad cap across the feedback resistor. It's for bandwidth limiting and square wave response. Well, here's the thing, it's for bandwidth limiting, but if you build a snubber out of it, in my case, it's a 10 or 15k resistor and a 22 picofarad cap. What it does is it still adds bandwidth limiting at around 500 kilohertz in my case to the feedback, but it also improves the square wave response. The other thing I found out was that this 10 picofarad capacitor from the VAS collector going to ground, it's not so much like a phase lag cap, but it helps to load the VAS down. It does something to, I forget what it was, a mid-band peak in the response or THD linearity. I can't remember what it was, but so I added that. So then don't forget my output stage was already a triple Darlington, so it's that stage that I just showed you. This driver stage was redesigned, I showed it to you on paper. So I've now got my beautifully designed output stage, pre-driver stage, and an amazing input section. And this is where I fucked up. I then said to myself, I'm sure Doug Self's Blameless amp would be great, so I'm just going to take my output, my driver, my input, and just stick his VAS in there. And that's where everything turned to shit. Since doing that, even on breadboard, I could tell that I was missing gain and it wasn't linear, which I know you can fix that with doing things like adding a diode into various locations or creating offset and stuff like that with the rails, with the VAS transistor, with the input pair, emitter degeneration resistors. There's a lot of ways of fixing that, but I started to discover stuff like that. And then once I got it on board like this, I started to discover that it's really unstable. And as I've shown you in the last video, I'll just show you again quickly. I did research into this. I read a lot of papers from Doug Self, papers from other people who've built the amp. And something I found out was, well, I already know that the VAS transistor is going to have poor ejection from the rails and all that sort of stuff, simply because it's going straight to the rail. There's no current sink or anything there, no current mirror, nothing to get it off the rail and provide that resistance from the rail. So it's very susceptible to current pulses and noise on the rail, which is what's going on here. It's mucking it up. And I didn't realize this at first. I could tell that there was some sort of resonating problem when it tries to start up and two sides try to come on to establish bias, and they're fighting over each other, and the caps are charging and discharging, and the power rails are resonating. But it wasn't until I lowered the resistor values, the filter resistors, RCs, it got worse. But when I added a current source to the VAS transistor, it got better. And that's when I realized something. Everything's actually fine. It, again, is the VAS transistor. So this little emitter follower beta enhance VAS setup, whilst it's good for getting gain, and it's, you know, the beta enhanced transistor hung off the 0-volt rail, great. If you don't put a resistor in its collector, it doesn't act as a transconductance amplifier on its collector and vary its capacitance, creating a Miller effect. It just gives you extra gain. It's great. And to improve linearity, you put its emitter to the negative volt rail with a fairly high value resistor, in this case GK2. Anyway, nothing wrong with that, but I would argue that there should be a current source there, and I'm going to add one probably. But the VAS transistor, it's just, I don't agree with it. Like I said, I'm thinking symmetrical VAS for the next amp, but for this I'm going to try and come up with a solution, not a band-aid, a solution to get this to work. If I can't get a solution to get it to work, and it's going to be a band-aid, I may wipe all the components off this section of the board, or bar the current sources at the top. Like, I might make another board or something that sits over the top and make a symmetrical VAS stage. I don't know. We'll have to see. But anyway, I just wanted to show you this on the computer. So, where am I? What? What's going on here? The Hummingbird amplifier has disappeared. Alright, notice I pointed this out in the last video, 47 ohm resistor here and the capacitive couplings over here. However, look here, you've got your VAS transistor, 47 ohms right before it, capacitors to ground, and then a resistor to it. These people knew that this has a stability problem and this is the band-aid for it. Well, the 39 ohm resistor actually acts as a current shunt for this current limiting circuit, but it does also give emitter degeneration. It also gives damping and acts, you know, to provide resistance on top of the RC filter here. So it's obviously known that whilst it's a good design, that part's flawed. So I'm going to try and come up with a PNP current source or an NPN current source, one of the two, and see if I can get it to actually work. Need to work out this stability issue, and yeah, let's just hope we can get there. If it really seems to be too unstable, I've already thought about this. What I will do, I'll disconnect the input stage, disconnect the feedback, and I'll put a current source coming from the collector of the drive transistor. Just like there's a current source going to the collector of this one, I'll put a current sink there. I'll set them both the same, power the amp up, and see if it's stable, just with current sources, drivers, and bias network. If it is, I think we're going to go symmetrical VAS. And yes, I'd already decided halfway through doing this that I'm going to take this all the way and make it full high end. Even like these capacitors will end up getting changed for high grade films. Resistances will have to change to compensate. You know, like feedback capacitors are polystyrene, transistors are the best you could get. I'm going to even add regulation and filtering to the rails. I just need to sort out this problem first. Basically, I've looked at like at least 50 different amp designs and thought about what I like about all of them, and that's what this is. I'm basically trying to build, or not trying, I am building a really high-end amp bit by bit by taking a few designs that I've come up with, mashing them together, and then working on it until I can perfect it, and then I'll keep adding to it until it's finished. And I will say this, it might seem annoying that like it didn't work as good as it did on breadboard straight away. Yeah, but to be honest, I have a problem working on breadboard once things get to this level of complexity, offset currents, high input impedances, stuff like that, current flow. You just bump the breadboard, oxidation between connectors, everything turns to shit. Your output devices can go up in smoke just because you went like that to the breadboard. It's no good. I'd rather actually get everything working as at least to this point, and then the little bits I need to work on, I can, like this, still work on breadboard off to the side, or if it's just one or two components, just solder them in or out. I designed my PCB so I don't have to go through, so I can just solder from the top and lift it off like surface mount. So that's my philosophy on that. So I just hope that answers everybody's questions as to what this is, how I'm going about it. Yes, there's still a lot more to go. Well, there's not too much more to go, actually. There is the VAS problem to solve. Then I want to add some sort of filtering / regulation to the rails. Then I want to add VU meters, DC offset protection, external current references for all the current sources, possibly a snubber network for the bias string diodes. And as I said, input, because it's a CFP input, the resistance can be increased and the capacitors can be decreased. But I want to see the quality trade-off of noise and THD with increased input resistance. I might meet in the middle somewhere. Something I've found in audio design is some people will say like do this, or some people say do that, and I've always found in the middle seems to be the best. Anyway, we'll work that out. And I also still want to investigate that 1.4 meg resistor across this cap here and other values and see if it does anything to that mid-band peak, if it even exists. Went over that in the OITPC video. But anyway, so that's the design philosophy. That's what's going on. That's my thinking behind everything. These are individually 250 watt channels. They may end up doing 350 watts a channel. If they do that, I'll end up taking the 150 watt output devices off and put like I've got MJL 21193s, 21194s. I've got NJW 1302s and 3281s. I've got transistors for the job, so that's fine. But yeah, I wanted to build an amp that's high end and high power at the same time. Not one of these amps that's got, 0.005% THD when the volume's at 1 watt, and then, 1% THD at 100 watts and 10% THD at 500 watts. I want quality the way through. That's why I'm overdoing everything. Another thing I want to point out is my power supply design philosophy, because a lot of people overlook this. And current path sharing. So, like if you look at the output stage, for example, you'll notice that between the collectors is an equal sized track, and the connection point's right in the middle of it. You'll notice that everything's done very symmetrically. Power wires are measured symmetrically. The drivers have got their own wires. The outputs have got their own wires, so there's no current pulses going through the same wire that another transistor is running off. Separate grounds, so there's a ground for all the stuff that's coupled from the positive rail and the positive circuitry to that ground. There's a separate ground for all the negative half stuff. There's audio grounds for each channel that's 10 ohms off main ground. Just wanted to point all that out too. I've put a lot of thought and time into this, like a lot. So anyway, that's all for this video. Like I said, it wasn't going to be long. It's just to answer your questions and design philosophy, whys, whats, hows, that sort of thing. So thanks for watching, and honestly, if you have any suggestions or comments on anything, leave it down below. I'm all ears. But till next time, I'll see you all soon, and thanks for watching.